last talk of the summer school, probably talking about entropy.
So I wanted to first I wanted to finish this discussion of the two of this geometry. So the geometry consisting of two black holes which are connected through a wormhole. So we talked about this ER bridge, and we also had talked that we can interpret this geometry as an entangled state of two systems and of two black holes. And in this case, we can think of this geometry as describing an entangled state of the an entangled state where we sum over all the microstates of one black hole and all the microstates of the other black hole in the particular thermophile double state we discussed before. So the idea is that if we knew what all the microstates of the black hole are, then we could sum over all the microstates of these black holes. And then, so these are states which are localized here. These are states which are localized here. We consider this particular entangled state, and the idea is that this particular entangled state is described by this geometry. So this is a kind of EPR state, a very complex EPR state where we sum not only over two states, but over a large number of states. And so this connection, we called it sort of ER equal to EPR, in the sense that in these gravitational systems, when you entangle the black hole microstates, you actually the entanglement gives rise to a geometric connection between these two systems. So from the outside, they look like entangled states, but in the inside, they are actually connected to each other, and they are at a short distance from each other. And in both cases, you cannot send signals from, so here from the outside, if you remain outside the two black holes, you cannot send signals through these wormholes. So an observer here cannot send a signal. And that's consistent with this entanglement interpretation. Now you could wonder, so this is true, well this probably is true, and the arguments that is true for this case of two entangled black holes are reasonable, fairly reasonable and convincing, and most people are convinced about that. There is an issue of whether you can actually make these states. It is very difficult to produce entangled states, and to produce an entangled state with a huge entropy, a huge entanglement entropy is even more difficult. So you could question whether it's actually possible to do this. I will not answer whether it's possible or not. Maybe it is impossible, but if it were possible, this would be the interpretation. It seems certainly possible to do it in the AdS CFT context, where these are states that live in the boundary theory, and then you can produce any entangled state you want in principle. So in principle, you should be able to produce these geometries. Now, one question you can ask is, imagine that how general is this? Is this valid when the black hole, for example, is entangled with a bunch of spins? And the answer is we don't know, but it might be that that there is always some kind of geometric connection. But of course, near each of these spins, we cannot have anything that resembles classical geometry. It has to be whatever very quantum geometry. But then maybe all these very quantum spaces join to form a smooth bridge that connects to the space that you have here. Yes?
How does the black hole get entangled with the spins outside?
Right, so that's a different, so here, yeah, good. Here I'm taking the point of view that someone tells you that they are entangled, right? And then we are trying to find the geometric description. In practice, one way to get them entangled is to start from a black hole and let the black hole evaporate. So it will emit radiation. And let it evaporate for a very long time so that it emits, let's say, more than half its initial entropy, right? So if this evaporation process puts you in any generic place in the Hilbert space, it will produce a state which is maximally entangled between the remaining black hole and the radiation. Because if you have, so if you have two Hilbert spaces, H times HB, and you take a random state in this Hilbert space, the space, and let's say the dimension of this one is smaller than that one, then the state will be maximally entangled in the sense that the reduced density matrix on the guy that has the smallest dimension will be of order 1. Will be 1, the identity, close to the identity. Okay, so so that's one way of producing. So in that situation, if you assume that the natural evolution of this system will produce a fairly random state in this product Hilbert space of the black hole, the remaining black hole and the radiation outside, then you will be left with a situation similar to this, where instead of spins we have the radiation. But we can transfer, if you wish, the state of the radiation to the spins. Okay, so this is some speculation. So the speculation is that in general, whenever you have entangled states, you have some kind of geometric connection. The geometry could be very quantum and very different from classical geometry. And in some cases, it is an actual classical geometry. Very good. So that kind of finishes the discussion of today's lecture, which was mostly about gravity and how entanglement is important for black holes and some of the weird aspects of entanglement. Of perhaps the weirdest is this story about the eternal black hole, or this maximally extended Schwarzschild geometry. So now I thought I would give I'll talk about some things which involve entanglement and so on, which happened in the last few years, which might be of slightly more direct interest to you. Yeah.
Can I just clarify this discussion? So,
yeah.
I guess earlier in the day you had this picture where degrees of freedom outside and inside the black hole were supposed to be maximally entangled, but also you were saying these are supposed to be entangled to some spin system.
Yeah.
So here.
Right. Yeah. So the idea is that if you had the black hole entangled with the spin system, then the question is whether that would have a smooth horizon or not. And then the idea is that you, So let me before answer, let me answer this question going back to this situation. So here we have two black holes which are entangled with each other, right? And then we can ask, well, how could this be if in this region we had some quantum degree of freedom which is supposed to be entangled with the guy here inside? So how is this compatible with the fact that this guy is actually supposed to be entangled with some degree of freedom on the other black hole, right? And it is compatible because this degree of freedom is entangled with this other degree of freedom on the outside of the black hole, right? Of the second black hole. But this one comes just from the time evolution of this guy here. So it is fine to be entangled with the time evolution of this black hole, right? So this one is not an independent degree of freedom, but it is the same as this guy, right? So from the outside, it looks like this object is entangled with something outside the black hole. But once we go to the interior, we're just seeing this original object which was entangled with this is just evolves and becomes the object you care about. There's no problem with having this triple entanglement in a situation where they are causal. I mean, if you have a spin here and the same spin in the future and some other spin here, right? These two can be entangled, and this is entangled with this, and this is, of course, entangled with that. So that's no problem. And the reason this can happen here is because you have this geometric connection through the interior. So the fact that the horizon is smooth and that you have some entropy of this guy comes from entanglement through a smooth horizon is not incompatible with the fact that this black hole is entangled with the second system outside. And the idea is that, so the reason we were thinking about this is that in this situation, you could have a somewhat similar picture where you don't have now a right-hand side which looks geometric at all, but you have some kind of mess here on the left side, which is where all these spins are coming in. But if you, but this degree of freedom which you see inside is some complicated combination of the degrees of freedom of the various spins, right? So that they are not independent. The idea is that they are connected. This one is connected through the spins through the wormhole. So it's not connected. So it's far away in the spatial, in the usual ambient space outside the black hole, but it's connected through this wormhole to the interior.
So do you want to say that the locations of the spins are actually sort of identified with the corresponding bit inside the black hole?
Well, the locations from the outside point of view are far away, but there is this dual geometry. So it's not the geometry of the original space, it's some extra geometry which connects them through the interior.
But do we want to identify this other geometry with the actual space?
No, no, you don't. In the same way that this interior is not identified with the exterior, right? So there is no exterior. There is something coming out of each. So coming out of each spin, there is a very quantum geometry that then connects all the other spins. So it's something that does not occur in our space. It's some extra dimensional space, and that could connect to the black hole interior. This is a very speculative idea whose details are not understood and so on, and it's part of what people are that we are trying to understand. Most of the things I talked about in my previous lectures are well understood. This is pure speculation. So I'd like to. Are there more questions about this? Yeah.
What do you mean, smooth horizon? Maybe you mentioned.
Yeah. So smooth horizon is just one where if you have an observer who falls in, this observer does not feel anything special when he crosses the horizon. That's what I mean by a smooth horizon. So where nothing special is happening.
In contrast to the firewall.
Yeah, in contrast to other things people might talk about, that the geometry is changed at the horizon. Yeah. So in general relativity, a black hole has a smooth horizon. So
the psi is just a state of two black holes which are entangled between
yes, yes. So the idea is that this state describes this geometry, this connected geometry. Well, the geometry that I had here before. The eternal Schwarzschild geometry, or the two-sided Schwarzschild geometry. Okay, so now I'm a little split. So I could. There is a very fun application of entanglement entropy, but this is just in the context of quantum field theory, relativistic quantum field theory, which is the application to the C theorem. And I could talk about that, or I could talk a bit more about the root Takayanagi formula. Do you prefer any of these two topics? Okay, so I'll do both first. So this is some example. So we are going to be doing conformal field theory, quantum field theories in 1 + 1 dimensions. Okay. First, let's consider a conformal field theory, and let's consider the. So this is the one space dimension, and let's consider the entanglement entropy of some finite region A. Now it turns out that the entanglement entropy of such a region is equal to C/3 times the log of the length of this region. So let's say this is the length of the region, divided by epsilon, where epsilon is the UV cutoff. And C is some constant that characterizes the CFT and is called central charge. Well, C is some constant that characterizes this two-dimensional CFT, and it appears in various places, like in the two-point function of the stress tensor. So it behaves. The two-point function of the stress tensor behaves in this way. But there are some indices I'm not writing, but anyway. And it also characterizes the conformal anomaly of the theory when you put it on a curved background. So the point here is, first of all, notice that the divergence is just additives log of epsilon. So I said in general dimensions, we get a divergence that goes like 1 over epsilon to the dimension minus 2. In 2 dimensions, this becomes a log. Okay. And okay. So that's a result in conformal field theories, and you can get it from by some conformal transformations of the result for the infinite line. So for the infinite line, we found this thermal density matrix, and then by doing conformal transformation, you can send infinity to a finite location, and we get some entropy from the conformal anomaly. I'm not discussing all the details. I'm just making it plausible. Okay, making it plausible that this could be the result in conformal field theories. Now let's go to non-conformal field theories. Okay, and let's consider this non-conformal theory to be a theory which has a conformal fixed point in the ultraviolet, which has some C ultraviolet, which is the central charge of that conformal theory in the ultraviolet. So in this theory, the entanglement entropy as a function of the length will be a non-trivial function of the length of the interval. There will still be a C UV over 3 log of 1 over epsilon UV divergent piece. So that's the UV divergent piece. But then there will be some finite function of L, okay? Which in the conformal case, it's just log L. But in the general non-conformal case, could be anything. Okay. Now, turns out that there is something. So I mentioned before that there was some interesting properties of finite pieces in entanglement entropy. And this will be one of them. So we can define some, let's say, I'm calling it the entropic C function. Well, it was called like this by the authors of the paper I'm describing, so which were Cassini and Huerta. So Cassini and Huerta are the authors of the work I'm describing now. So we can define this particular derivative. Notice that if the theory is conformal, this particular derivative will give us the C, the constant C that we had over there. In addition, the infinite piece doesn't contribute because it's independent of L. So the infinite piece just depends on the endpoints of the interval, and it's independent of the length of the interval. Right? So this is a nice thing that is calculable in the theory. And if we flow from, let's say we have some UV conformal field theory at high energies, and at low energies flows to an infrared conformal field theory, this, in the two values, this quantity would become CUV and C infrared, which is the central charge of the infrared theory. Now, the nice point is that we can now use these concepts of strong subadditivity plus special relativity to prove that that quantity that we define here will always be decreasing under the RG flow, so that C entropic, this decreases under RG flow. And okay, so this is something that puts a kind of order in the possible conformal field theories, because it tells you which conformal field theories could in principle flow to other ones. So if you have some conjecture that a certain field theory, in the infrared flows to some other one, you check whether the C infrared is less than the CUV, and then you can test whether your conjecture was correct or not. But so this is something that this final result is something that some logic had proven by considering the 2-point functions of the stress tensor. So it was proven a long time ago, maybe 30 years ago. But I'm describing this, this way of arguing because it involves entanglement. And it's a very nice argument. So you just look at the region. So this is some interval. And I'm drawing just the future light cone of this interval. And so this is some region. And then we could consider a smaller, so some other interval, which is shorter. And now we're going to define various regions. So we're going to define region, this we are going to call region A, associated to this tilted interval. So one is time, and the other one is space. Okay. Then we can define region B will be this interval. And this guy really can, yeah. Now, if we consider this interval, we can do this interval really is in the intersection of A intersection B. So it can be sensitive. So so the observations on this interval are so we take an interval like this, we can observe anything to the future, and yeah, maybe I'll first draw. So if I have an interval, I can, I can draw this type of space-time diagrams, which tell me the whole region where I can insert operators, and any operator in this region can be transformed by, let's say, the Hamiltonian to some operator here on the interval and can be measured, and it's part of my observable algebra, right? My algebra of observables. So anything that I can measure in this interval, I can measure both in A and in B also. And this bigger interval contains both A and B and is A union B. Now, the entanglement entropy of each of these regions, A union B, A union C, etc. Well, first let's consider the strong subadditivity condition that we feature prominently in Libb's talk, which says that entropy of A union B plus entropy of A intersection B is less or equal than entropy of A plus entropy of B. Right? And now we apply it to these intervals we were discussing. And then we use special relativity to argue that the entropy only depends on the length of the interval, on the proper length of the interval, not how it's tilted in Minkowski space. And we further, just for simplicity, let me call this value of the x plus coordinate, let me call it 1. Or let me call this guy 1. And then this will be bigger than 1 by, let's say, an e to the delta, this piece. So this is also 1, and this is 1 e to the delta. And so the length of the various intervals are, so for example, A union B is S of, and then we multiply the x plus times x minus and take the square root. So we get e to the delta. The A intersection B is just 1 times 1. That would be, the length would be just 1. And the other two, which have equal length, and is twice the entropy of length e to the delta over 2. Okay. Now let me define a function of x, which is s of some length, which is s e to the x. So then this is just some function of delta plus f of 0 to f of delta. Okay. And now we expand in powers of delta, and then we check that, let's say, when delta is actually equal to 0, this becomes an equality. To linear order in delta, this also is an equality. And then to quadratic order in delta, what do we find? We find f double prime delta square over 2 here. And here we find twice times f double prime delta over 2 all squared, one extra factor of 2. So there are more factors of 2 in the denominator here than here. And so what we've proven is that this f double prime is less or equal than 0. Okay? So in other words, strong subadditivity implies this f double prime is less or equal than 0. And notice that this definition is equivalent to saying, so this definition is just f prime of, and so what we've proven is that f double prime is 0. So f double prime is saying that the LDL of this C entropic of L is actually less or equal than 0, right? So we've proven that this entropic C function decreases under normalization group flow. As we take the interval longer, this function decreases. Okay, so what's cool about this proof is that it uses, first of all, it defines the quantity under consideration in terms of entanglement entropy, so which is a direct count of the number of degrees of freedom. And then it uses very general properties like strong subadditivity and Lorentz invariance to argue the desired result. And so in 2 dimensions, this was a known answer, but this style of proof can be extended, and it was extended by these authors, to the 2 + 1 dimensional case, where it is not known how to prove it in some other way. And there, what one considers is the entanglement entropy of a circular region of size R. Okay, now we are in two space dimensions. And in these 2 space dimensions, we can have the entanglement entropy of this region. In a conformal field theory, we'll have a divergent piece and then a finite piece. Okay, R is the size of the circle. And the statement is that we can define a function f, which is, let me get the sign right, is r dr minus 1 times s of R. Notice that the divergent piece cancels out in this, and we'll just get, in this case, we just get minus this finite piece. And they've proven using similar ideas that this function decreases under normalization group flow. And this finite piece is also interesting even in topological field theories and can be used to characterize topological phases of matter and so on. So if there were papers by Kitaev and Preskill and Levin and Wen who proposed to use these finite pieces of the entanglement entropy of circular regions to as an order parameter for topological phases. Anyway, so these are some what I consider fun applications of entanglement. Okay, that finishes this discussion. And well, the final topic I wanted to mention is this Ruta-Kayanagi formula. So this is a formula for the, so if you have a quantum field theory, that has a gravity dual, then here is the space where the quantum field theory lives. And this is the holographic direction or direction C. And then if you have some region A here, so and you want to consider the entanglement entropy of region A in the quantum field theory, in general, computing these entanglement entropies in the quantum field theory is rather difficult. You have to work hard to compute them. Even in free theories, it's difficult. But in a theory that has a gravity dual, there is an extremely simple prescription for computing it, which says that the entanglement entropy of region A is equal to the area, minimal area in the bulk, area min over 4g Newton. So you take a surface in the bulk, which ends on the boundaries of the region, and you minimize over all possible surfaces. You minimize the area. Take this, the one that has the minimal area. And this is supposed to be an approximation in the large n limit for the entanglement entropy of this region. So it's a very, very simple answer. And because it's a simple answer, people have computed it in a variety of circumstances. It's very useful for testing conjectures you might have about what entanglement entropy might or might not do. So in strongly coupled systems, you can compute it in this way. So in this particular strongly coupled theories. So you have some conjecture of what entanglement entropy could do or not do, so you can at least check it in these cases. Yes?
Sorry, in 2D CFT is only geodesy, the length of geodesy?
Right, right. So in the particular case of 2D CFT, so which is what I essentially drew in the blackboard, there is one spatial direction and one extra holographic direction. This is a semicircle, and it's the length of the geodesic, and it's essentially the same calculation we discussed a couple of lectures ago, where, remember, we got a log. So we got a log of the length of the region divided by some UV cutoff. And then in this particular case, we get the radius of AdS3 divided by G Newton. And this is this quantity C we discussed before. So we get the same as what we expected for a generic two-dimensional field theory. In this case, in conformal field theories, this result in two-dimensional conformal field theories is completely determined by the symmetries. Notice we did almost nothing. We just took the circle, and it didn't depend on any details of the metric or anything like this. And indeed, it's determined by the symmetries. But if you consider more complicated setups, like, for example, two intervals, right? And then things can get a little more interesting. So, for example, for two intervals, so we'll have interval A and, let's say, the interval B. You can compute, for example, the entanglement entropy of A will be this, the entanglement entropy of B would be this, and you can ask what is the entanglement entropy of A union B, for example, right? And if they are very separated, so you have to consider a surface which ends here, and these two surfaces actually are an example of a surface that you could consider. If the intervals were closer to each other, so let's say this is A and this is B, it might be more convenient to draw them like this. So in that case, you might have a different answer. And you can consider the mutual information between A and B, which is S of A plus S of B minus S of A union B. And you notice that in this particular setup, that is actually equal to 0. And in this other one, it will be bigger than 0. This thing has always should always be bigger or equal than 0. And so in the large n approximation, it's actually exactly equal to 0. If you consider the sub-leading corrections to this formula, then you find some result which is bigger than 0. Yes?
What determines the choice I use?
Yeah, I'm supposed to choose the one which has shorter length, smallest length. And it turns out that, yeah, it doesn't follow from what I'm saying here, but it turns out that when the two intervals are close to each other, this has shorter length. And some of the perhaps more non-trivial applications of this. Oh, let me just give you one fun. So Elliot Lieb emphasized the fact that it is very difficult to prove this inequality. You know, it's very subtle. There are many proofs, people claiming to prove it, and so on. So let me prove this inequality in this particular context. So imagine you have the strong pseudo-additivity inequality. So you have region A, which is this. Let's say region B, which is this. And then this will be A intersection B. And this whole thing is A union B. Okay? So let's look at the surfaces here in the right-hand side. So will be, this is the thing that computes the entanglement entropy of A, is the length of this line. The entanglement entropy of E is the length of this line, right? The entanglement entropy of A union B will be something like this, and of A intersection B will be some, sorry, this is A intersection. Let me draw it in a different color. No other colors. Well, can you see this line here? And then you have this other line for A union B, okay? And what we are supposed to show is that the sum of the length of these two is less than the sum of the length of these other two. Okay? But notice that if here we disconnect these two and we just put them like this, right? And then we let them find, so the length of this disconnected one is exactly the same as the length of the right-hand side here, right? So when we move them to these other options, we can only lower the length because these two curves were defined to be the ones with lowest length, right? So we automatically will obey this inequality. Of course, this is not a proof of the this is not an alternative proof of Elliott-Libb's result. I mean, it's just simply a proof in this context, in this approximation. So in the large n, it is only valid for large n field theories and strongly coupled field theories, okay? And for the leading order term. Okay, but it just shows how some of these properties become very simple geometrical properties. And so we think that this very simple formula, which is a close cousin of the black hole entropy formula, is telling us something about how the gauge gravity duality is supposed to work and how space-time, how the degrees of freedom of space-time are supposed to be captured and so on. And I probably, well, there are many more things you could do with this Ritika formula. Some of the interesting things include, for example, considering starting from complicated states and watching how they thermalize and how entanglement propagates from one side to the system to the other side and so on. All the things you can do easily because you can really, it is a simple matter to find these minimal area surfaces. And so you can do all these entanglement calculations in a simple way. But I think I'll end here. Thank you.
Do we have any questions?
Yeah.
One stupid question, but is what was the responsible?
Yeah.
The triangle where you have A and B.
Yeah.
How did you decide the lengths of those curves? Like the length of A, for example? You said it was.
Yeah, so maybe that was a little fast. So. Yeah, so these are Lie-like coordinates, right, from this origin. And so the length of A is the product of this length times this length, right, which was 1 times 1 times e to the delta, right? So that's the square of the length, and the length is the square root of this, which is e to the delta over 2. So we are using, this is in Lorentzian signature. We're using this geometrical facts about Minkowski space. Okay.
Any other questions? Then let's thank Professor Maldacena.
Okay, thank you. Thank you. Thanks a lot.
That concludes the summer school. On behalf of the organizers and the speakers, we thank you for attending. Hope you had fun, learned something. Hope you get home safe. And
thanks for organizing.
Yeah, no problem.
Yeah, I think as the last speaker, we should thank the organizers.
And these schools happen every year. The topics change. So just be on the lookout next year for the next school. All right, thank you.